We are here to present the work Step Change Detection based on analytic signal for PMU calibrators. I am Marcelo, and the other authors are Renata and Paulo. We have made this work at the installations of INMETRO in Brazil. So first, I'll give a brief introduction of the context, some math to explain how we define our models, or mathematical models, or detection signals, and we define a hybrid detector for the step change. We made some numeric simulations to assess the performance of the step change detection for the step location and for frequency estimation, and some laboratory measurements to validate the procedure. So, we want to assess PMU calibrators. In the National Metrology Institute, we wish to have reference values for synchrophasors, for PMUs, and we want to have it with low uncertainties because we need to assess PMU calibrators. These PMU calibrators must be compliant to the standard IEEE, I'll call it IEEE standard. And among those tests, we have dynamic tests, and among dynamic tests, we have step tests of magnitude and phase. This is a brief of the parametric model that I will explain later, but in a previous work, we have developed a procedure using this parametric model to estimate each one of the parameters that I highlighted in blue. And we use an iterative procedure called Levenberg-Marquardt iteration to estimate each one of these parameters, but the step location. Okay, in a calibration system, usually we give the nominal values, and we have a voltage generation and sampling of the signals, and after that we have some kind of analysis. And the hardware tasks, they will introduce errors, uncertainties, and noise. So each algorithm we use for the analysis needs to be assessed regarding errors and uncertainties and also noise, so we can have a way to assess the behavior of the hardware. As I said, the Levenberg-Marquardt iteration estimates the parameters from this model, and also what we call the underlying frequency. But it needs reliable and accurate estimates of the step location and when initial guessing for the underlying frequency. For the step location, we used an estimation of step location based on instantaneous frequency of Hilbert's analytical signal. And we faced some special cases. The first is magnitude steps occurring near zero crossings, as we can see here, and also phase steps occurring near crests, like here or here. And in this work, we will face these special cases for the step location with a hybrid detector, which is based on instantaneous magnitude and frequency. Here we use it only the instantaneous frequency, and now we use the instantaneous magnitude and the instantaneous frequency. And also we can give an estimation for underlying phase of frequency, which can be initial guessing for the Levenberg-Marquardt iteration. So, in the continuous time, we have an analytic signal, Z, which is formed by a signal, X, and its Hilbert transform given by this equation. From the analytic signal, we can have an instantaneous magnitude signal and an instantaneous phase signal. From the instantaneous phase, if we get the derivative, we can have the instantaneous frequency. If we get the input signal X and do sampling, we have the discrete version of X, and with the fast Fourier transform of X, discrete X, we can have the Hilbert transform of X and a discrete version of Z. A discrete version of the analytic signal can be obtained by fast Fourier transform. And by the numeric differences of the phase, instantaneous phase, we can have a discrete version of the instantaneous frequency. So we can have discrete version of each one of these signals that we will use in our detection procedure. So now we define formally what is our parametric model given by this equation. Xm is the initial magnitude, Kx is the percentage of the magnitude step, U is the unit step function, phi0 is the initial phase, Ka is the amplitude of the phase step. I highlighted in red what we are working in this work. Tau is the step location, instant of the step occurrence, and Fu is the phasor underlying frequency. And also we have a function, a random process representing noise, eta. So for a zero mean white Gaussian noise with standard deviation of x given by sigma x and the prescribed SNR in decibel, we can have the variance of the noise as given by this equation, and we can have a model to represent the noise in our parametric model. And now we define detection signals. So to detect the step location, we define from the instantaneous magnitude, we get the first order differences and define a detection signal called dm, taking the modulus of the difference of the first order differences and its median. So m here is the median operator. And we define also a threshold given by lambda m. So we have km times the median of the detection signal, and km is a scalar. From the set of indexes n for which dm is more or equal to the threshold, we get a value called dm max, which is the infinity norm of the detection signal. And we have a candidate index. The candidate index is the index for which, included in nm, the index for which the detection signal has its maximum value. Likewise, the step detection via instantaneous frequency, we will use the first order differences of the theta signal, the phase signal, instantaneous phase signal, which happens to be an estimate of the instantaneous frequency. We define a detection signal, we define a threshold in a scalar kf. We define a set of values for which the detection signal is greater than or equal to the threshold, and a maximum value given by the infinity norm, and we have also a candidate index. From these two candidate index, we calculate two ratios. So first we set the parameters Km and Kf using some criteria, and we have the candidate index and their respective ratios. Ratio from the DM max and the threshold. The highest ratio, we understand it represents more information. So its index have here n hat will be the index with the highest ratio. So the step location estimator from the hybrid detector will use the candidate, the index with the highest ratio to calculate tau, to calculate an estimate for tau. And also we can have an underlying phase of frequency estimated by the median of the instantaneous frequency. To assess the performance of the hybrid detector, we chose first Km and Kf equal to 3, which represents outliers greater than 2 sigma, 2 standard deviations. And we assess the accuracy under noise conditions from signal noise ratio 30 to 60. And we made some Monte Carlo simulations. Each run we generate one frame, one signal with 480 samples with a frequency, sampling frequency of 4,800 Hertz. So we have this sampling interval. We use the underlying frequency of 60 Hertz and we place the step in the middle of the frame with 240 samples. And we simulate for 3 different cases. The first one is a single magnitude step with 10%. The second is a single phase step with 10 degrees. And the third is simultaneous steps when we apply cases 1 and 2 simultaneously. The metrics for the performance, we take the errors in the estimation of step location, and then we take as false positives for this estimation when we had an estimation but its errors are considered high, and for false negatives when we have no detection of steps, but we do know that there is a step because we generated the signals with the step prescribed in the 3 cases. So after all the Monte Carlo simulations, we get the percentage of total failures for each case, for each noise condition, and for each signal as the sum of false positives and false negatives divided by the number of Monte Carlo simulations. And we get also the frequency error. These two are highlighted in blue. We will show the results. So for the first case, remember it's a single magnitude step, we get the percentage of total failures. Consider a confidence level of 95.45. We see that when, for the magnitude step, when we get near to the zero crossing, we have more failures. And when we have more noise, also we have more failures. I highlighted in green the situations when we consider it is acceptable, consider this confidence level. So most of situations it is acceptable. For the second case, when we apply a single phase step using the same procedure, we can observe that we have more failures when the initial phase produces the step near the crest, and we have less failures when it goes far from zero. When the initial phase goes near 90, it is easier for the detection to estimate the step location. And when we go to the third case, we have a mix of the two performances, and we have a better performance for most of the cases, and also for 30 dB, but we have more failures near the crest and near the zero crossing. So we have a mixed result as a result of using both detectors at the same time. And for frequency estimation, we have observed some bias. Here we have for case 1, and also variances depending on the noise level. So noise degrades the performance, and we have very crude estimates of frequency. We have bias in all three cases. We have bias as the mean values of the frequency error, but these values can be used as initial guessing for the Levin-Bergman-Quart iteration, which can bring us much more accurate results. And this is the laboratory setup we are developing at INMETRO to serve as a PMU calibrator and also a calibrator of PMU calibrators. So to validate this procedure, we have implemented it in a PXI system, which is shown here. It is capable of generating and sampling signals with the same time basis, which come from an atomic clock. And we have a CPU here that can perform the analysis we showed in the last slides. To have this first validation, the circuit is generation and sampling is connected directly. So for now, we are ignoring the influence of the voltage amplifier and the resistive voltage divider, which will be used in the future to make the calibration of the device under test. But now we are making a direct connection. And here we have some measurements which were made using this setup and the estimates using the procedure we presented. So for cases 1, 2, and 3, the same cases presented in the simulations. We have these measurements for the step location and these measurements for the frequency. We have an estimation of the system intrinsic noise. It means that we are not generating directly the noise now in the digital signal. The generation of the digital signal has no noise, only the noise produced by generation card itself. So we have an estimation. It is something around 50 decibel. And we can make some preliminary uncertainty budget For the step location, we know that we have an uncertainty of 2 sampling intervals. And for the frequency errors, we have 1 sigma that I got from the last tables, to see here. As we have bias and we have an estimation of the signal noise ratio, we can make a first systematic correction and have these measurements for frequency. As an example, using this as an uncertainty, of course we need to make more studies on the uncertainty contributions, but it is a first uncertainty estimates for these measurements. So now we formally define the hybrid estimator. It is capable of blindly detect and locate step changes. So now we can assess PMU calibrators and measure where the step changes are occurring. We have a simple estimator for underlying phasal frequency under step conditions. And now we are developing our investigation to, in the future, to simulate voltage sags with 2 or more steps inside the window and the implementation of denoising techniques. Thank you.